All right, so let's talk about conservation of momentum. When we were discussing just momentum in general, we said that this was mass times velocity. And then we talked about if an object's momentum changed, then it was usually because the velocity of that object changed. And we reviewed the idea that there must be a net force acting on our object in order to cause any change to its motion, also known as acceleration. And so then we kind of related some of the content that we've covered in the past, such as the vocabulary and formula for acceleration, change in velocity over time, some of Newton's laws, first law meaning that our object has inertia, so it's going to continue its motion unless second law says that a net force acts on it to create an acceleration. And so any changes in the momentum of my object must be the result of some force that was applied for a certain amount of time. So let's talk briefly about some of the different types of forces that may be exerted on our object to create that change in its momentum. So we have external versus internal forces, and they mean probably what you would assume they mean based off of the names. External forces are forces that come from outside of the system. So once we identify what our items or objects are that are being analyzed, then we give that object and its environment that is all together referred to as the system. So external forces are forces coming from outside of the system. And so whenever we have external forces, then the momentum of that system is going to change. The external forces change the momentum of a system. And so our example here is impulse, what we talked about in our last lesson, that we have a force applied for some time, and the result of that force is that the amount of momentum that our object has now changed. So a golf club hits a golf ball. So let's look at that. Our system in this case is going to be the golf ball. So that means that our golf ball has some amount of momentum based off of its mass and its velocity. In this case, we are going to assume that our golf ball has a velocity of 0. So right now, it has no momentum. Then an external force, the golf club, is going to come, strike the golf ball, applying a force to it. That force is going to create a change in its motion. And so now the golf ball is going to have some new velocity. Therefore, the amount of momentum that it has now changed, right? That's the idea behind external forces. So when we look at our illustration, we see here that we have the golf club, or they call it the club head, is going to strike the golf ball, and that's going to create an acceleration onto the golf ball. Now, I want to remind you that if we're just looking at our golf ball as an isolated system, the golf ball itself received a force. So let's say this is the location that the club hit it. It received a force for some amount of time. That force is responsible for creating an acceleration, which means that the object's velocity changed. So as a result of that impulse or that impact force, then my golf ball is going to experience a change in its momentum. Now, this is what happens with external forces. When we look at the slide here, it says something about the acceleration of the ball is greater because its mass is smaller. So in general, let's not forget that our mass and our acceleration are inversely related, assuming that our force remains constant. So now we want to talk about what do they mean by the acceleration of the ball is greater. Greater compared to what? Well, we are analyzing this right now as a system of just the golf ball. But I want to review with you that Newton's third law says that whenever two objects come into contact with each other, the forces exerted on those two objects are equal in magnitude but opposite in direction. So if we expand what it is that we are looking at, what we're evaluating, and we allow it to include the golf club, once again, when they make contact, there is a force that is exerted. In this case, there is also a force exerted onto the golf club by the golf ball. Now, Newton's third law tells me that the force exerted onto the golf club is the same as the force exerted onto the golf ball, except that it is in the opposite direction. So that force is going to be equal magnitudes, but it's going to be negative in value. This is a contact force, so the amount of time that the golf club receives the force is the same as the amount of time that the golf ball received the force. So if we were to change our question, and instead of analyzing the golf ball and its impulse that it received and its change in momentum, if instead we were to analyze the golf club, what we would find is that the golf club received the same force for the same amount of time, so it also is going to experience an acceleration. However, the golf club is going to have a bigger mass. Therefore, in comparison, the golf club will experience a lesser acceleration. So this last sentence is actually kind of leading us into the next type of force and thinking of a system that involves more than one object. So we will come back and we will revisit this concept, the application of Newton's third law, some more here in just a moment. But let's go ahead and now take a moment to define what internal forces are. So internal forces are going to be forces that come from the interaction of the particles within a system. So here's what this means. Now our system is not going to include only one object. Now our system is going to include two objects, and these two objects are going to interact with each other. So any forces that are applied that are responsible for changing the momentum of either of these objects came from within the objects themselves. So once we recognize what our system is, once we've identified our objects that are going to be included in this system, then the forces come from those objects. It's not some outside external force coming into our system and disrupting or changing the momentum of the objects. It is now contained within those two objects, basically. It says here that internal forces cannot change the momentum of the system. So don't get confused. This is not saying that the objects can't have a change in momentum. They are going to experience forces. There will be an acceleration. There will be a change in momentum. But this is saying it cannot change the momentum of the system. So now the pair of objects are going to collectively determine how much momentum we have between the two of them, and that amount is what will not change. So the amount of momentum available between our two objects is the value that is conserved, or is the value that does not change. So now we're going to be talking about collisions, things running into each other, interacting, bumping into each other. So when we use the term collisions, we're talking about some event where two objects make contact with each other. During a collision, we're going to ignore external forces. So again, this is why we say that our forces are internal. There's not some outside thing coming and affecting the motion of our two objects. Our two objects are going to be the things responsible for the force that is taking place or that is being applied onto the objects. Collisions usually happen very quickly. So if you just think real life, I mean, have you ever seen an accident? Have you ever been involved in an accident? It is a very quick event, right? It's just that moment that those two objects come in contact with each other. It's very common to see questions or hear examples where we're talking about maybe two pool balls that are interacting with each other. And so if that's the case, then you may send the cue ball across the pool table, but the moment where they interact is very, very, very brief, okay? Once again, Newton's third law needs to be reviewed and applied so that we can understand what is happening. So when we are talking about internal forces, when we're talking about collisions, object A is in contact with object B. So we are going to say that right here at this point of contact, there is a pair of forces that are being applied. Object A is going to exert a force onto object B, and at the same time, object B is going to exert a force onto object A. Because of Newton's third law, we know that these two forces are equal in magnitude but opposite in direction, meaning one is going to have a positive value and the other is going to have a negative value. They are both experiencing the forces for the same amount of time because it's a contact force, so they're touching for the same amount of time, therefore their time is equal on both sides. So what this means is that the impulse that object A experiences is the same impulse as object B, except object B's impulse is in the positive direction and object A's impulse is in the negative direction. So this tells me that both of my objects are going to experience the same change in momentum. The magnitudes of their change in momentum will be the same. But object B will experience a positive change and object A will experience a negative change, according to this example that we see illustrated here. So when we are talking about what our system is, in this case, our system is going to be the two objects that are interacting. So when we say that these two pool balls are going to collide, the forces in our interaction come from the pool balls themselves. That's what we mean by an internal force, okay? All right, once again, internal forces do not change the momentum of the system. So once we identify how much momentum the 7 ball brings to the table, and we identify how much momentum the 8 ball brings to the table, that collectively tells us how much momentum we have available for the system, and that total amount of momentum will not change. Now, what will happen is that when these pool balls interact, those forces are going to cause them to accelerate. So we will see a change in their individual momentums, but if we take those individuals and add them back up, we're still going to have all of that momentum accounted for, okay? In this particular example, since these are both pool balls, they have equal masses. So we're just kind of reviewing the application of Newton's second law here. If the force exerted on them is the same and the masses are the same, then in this case, they will both experience equal magnitudes of acceleration. All right, so when we say that internal forces do not change the momentum of the system, basically what we're telling you is that momentum is conserved. So conservation of anything, there's lots of laws of conservation of things in science. So conservation of anything tells us that whatever it is that we are discussing cannot be created nor destroyed, but it will be transferred or transformed into different objects, different forms. So in this case, we are talking about momentum. So we say that the amount of momentum available in our system does not change, but the momentum itself may be transferred from one object to another. So our total momentum before the objects collide is going to be the same value as the total momentum after our objects collide. Now, once again, if we understand Newton's third law, then it makes sense that the change in momentum is the same for both objects. So whatever one lost, it went into the other. So our total is remaining constant the whole time. So big picture is that the initial total momentum is the same as the final total momentum. If we happen to know the momentums of our individual items, then we would just take object 1 and object 2's initial momentums and add them up. And then after they collide, if we are able to identify their individual momentums, we would add these up and we would see that both the right and the left side do indeed give me the same total, okay? I apologize that these subscripts didn't come out correctly. Make sure that you understand that this is P for momentum, lowercase p, 1 for object 1, and a lowercase I for initial. On this side, this would be P1 final. So my 1 and my F are both subscripts here. Same thing for my extended version here. This should be M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Sorry, in the transfer of the electronic versions here, it doesn't copy those subscripts over correctly, but that's what it's supposed to look like. So there's two main categories for collisions. We have elastic and we have inelastic. Elastic collisions are collisions where my objects are going to collide, but then they're going to continue to move independently of each other. So my objects are going to stay separate, so that when we look at our equation, we have our first object, our second object, and they both have their own individual initial momentums. They're going to collide, and then after the collision, object 1 will have its own momentum separate from object 2. But once again, the total available does not change. It says here that the total momentum is conserved and the total kinetic energy is conserved in elastic collisions. Now, the opposite of this would be inelastic. Now, there are partially inelastic and perfectly inelastic collisions. We are going to be analyzing perfectly inelastic collisions. So this is a situation where my objects are going to collide, and then they're actually going to stay together. They're going to get stuck. They're going to mesh together. They're going to join up, however you want to word that. So when we look at our formula, in this example, we have two objects, or in this formula, it's setting us up so that we have two objects that begin initially separated. So they each have their own individual momentums. And then as a result of their collisions, their momentums are actually going to join up to form one. Because what happens is that these two objects are going to physically connect to each other. So it's essentially one more massive object that is moving with a single velocity. So it says here that they move with a common velocity. That's because they're stuck together. So of course, whatever the speed of the first object is, it has to be the speed of the second because they are now joined together. Now it says here that the total momentum remains constant for all collisions. Momentum is conserved, so that total value is going to remain constant. But our kinetic energy is no longer conserved. If we just think about what is happening in the actual real life event, it makes sense that we are going to lose some of our energy. Some of that energy is going to be used in the process of coupling these two objects together. So when we take into consideration kinetic energy is 1/2 mass times velocity squared, we will see that when we calculate our total kinetic energy for our two objects at the beginning and our total kinetic energy of our joined objects at the end, it is indeed not going to be the same value for kinetic energy. And a lot of times our kinetic energy is going to be lost in our perfectly inelastic collisions. Not always, but most of the cases, if they start off separate and then join together, that is what we will see. Now, the last thing that I have here is something called recoil, or you may hear them called explosion collisions. And so this is basically a reverse perfectly inelastic collision. So I have two objects that are going to give me a total momentum of 0. Now I want you to stop and think about this for a second. I have object 1 and I have object 2, and these two objects are going to add up so they provide a value of 0 kilogram meters per second. Now, you may be asking yourself, how is this even possible? Well, let's just stop and think about this. If I have a momentum, one in the positive direction and one in the negative direction, and I add those two things up, if those two objects have equal values for their momentum, then a positive 10 and a negative 10, you add them together, you get 0. So what happened in our recoil or our explosion collisions is that we typically have a situation. Now, the traditional way to see this is that our objects will initially be at rest, and then after the explosion, they then get put into motion so that one object begins moving in the positive direction and the other object begins moving in the negative direction. So when we consider our before, if they are both initially at rest, and then after they both have some velocity, but they're in opposite directions, this is going to come out to be some positive value for my momentum, and this is going to be some negative value. And it turns out that they're going to be equal magnitudes, but opposite directions, so they will still have a total momentum of 0. Remember, the main idea here is that conservation of momentum means the total momentum available does not change, okay? Now, I have an additional video where I've worked through some example problems for you that you can view if you choose. Really quickly, I just kind of wanted to show you the setup of these. So here we have elastic collision. I have two objects that remain separate. So here's object 1 with its momentum, object 2 with its momentum. This little dotted line represents the collision taking place. So in my formula, that's going to be where I set up my equal sign. And then in this case, they maintained that separate motion. So I'm going to follow the formula where it gives me 4 different places to put in my momentums because they were separate before the collision and they remain separate after the collision. Here is a second example, and you can see, or maybe you didn't notice in the first one, one of my objects was initially at rest. In the second example, all of my objects are moving, both before and after. So there is no stipulation about the direction of the motion or whether one's at rest and one is moving, or are they both going to the right or to the left or towards each other. Elastic collisions can happen in all different kinds of ways. You just simply need to understand that each individual object has its own velocity, therefore each individual momentum must be included in our setup of our calculation. Here is an example of a perfectly inelastic collision. So in this case, my objects were initially separate and then they joined together. So this is the traditional way to see it, but this is not the only way. We could also have perfectly inelastic collisions where my objects start together and then separate. So typically, that's going to be a situation where we have some sort of explosion. Sometimes this is called recoil. If you have any experience with firing a gun, you understand that there is a force that sends the bullet forward, and so we know the bullet's going to accelerate forward, but there is also a return force applied to the gun that pushes the gun in the negative or backwards direction. And so that's what some people sometimes call kickback or recoil. But basically, this is an explosion collision. This is a reverse inelastic or perfectly inelastic collision. So what I wanted to take a moment to show you here was that in this video, I review again in detail the application of Newton's third law, that these two objects are going to experience forces so that that force creates an acceleration. And so if you look at my little drawing up here at the top, my object that's sent to the right has a positive change in momentum, where my object here sent to the left or backwards has a negative change in momentum. And so these two are going to be equal in magnitude because they both experience the same impulse, so they're going to have the same change in momentum. They both were initially at rest, so VI is 0 in both cases, so their momentums after the collision is going to be the same. Now, when I look at my math work, you can see down here that I did the algebra. My initial side in this case had a value of 0. And so I had M1 V1 final plus M2 V2 final. My algebra requires me to move one of these to the other side. So I just wanted to show you, here's how my algebra sets up these two momentums. One momentum is equal to the other. However, one has a negative value because it's in the negative direction, and one has a positive value because it is in the positive direction. These are the different types of collisions that you need to know You need to be able to identify from a description or an illustration what type of collision we have. You need to be able to identify which is the correct equation to use in each of these different scenarios. And we should understand that in all collisions, we have conservation of momentum, so the total amount of momentum does not change. However, in perfectly inelastic collisions, the amount of kinetic energy does change. The total amount of kinetic energy does